All right, it seems that we are going live. So welcome all to the last talk of this morning session. So now we have James Hefford, who's going to tell us about hyper-decoherence in density hypercubes. So you have about 20 minutes to present your work, and then I'll try to put forward the questions that people will write down in Slack. So go ahead.
Great. Thank you for the introduction. So I'll be presenting some work that I've been doing with Stefano Gogioso on hyperdecoherence in density hypercubes. So there's three main topics I hope to cover during this talk. I'll start by giving a brief recap of what decoherence is and explain what we mean by hyperdecoherence and the formalism that we'll use to capture these two notions. I'll then introduce the theory of density hypercubes and explain how decoherence and hyperdecoherence arise within this theory. So what is decoherence? I mean, on a very just high level notion, it's the transition from quantum theory to classical theory. Since classical theory is a sub-theory of quantum theory, we expect there to be some mechanism which explains the transition between the two. And one standard description of this mechanism is given by sort of environment-induced decoherence, where a system interacts irreversibly with the environment, which leads to an irretrievable loss of information to that environment. And we can see that in the way that we draw these maps in the string diagrams of CPM. We have a quantum system A here that interacts with some environment, which we then discard. And there's three sort of main properties, main things we ask of such a map. Firstly, we of course ask that it returns classical theory in some sense, and I'll make this more precise in just a moment. Secondly, we ask that it's an idempotent map, so essentially that doing it twice is the same as doing it once. And that, in other words, once a system has become classical, subsequent applications of the decoherence map don't do anything. It just remains classical. And thirdly, we ask that it's a causal map. So this means that we can give the map a sensible operational interpretation as a map that we can implement deterministically within the theory. So what does this map actually do? Well, if we look at a density matrix, it simply zeroes out the off-diagonal elements in some basis, and we're returned a classical probability distribution. So how do we capture this in a slightly more categorical way? One way of doing this is to move from working in our original category, which was the category of completely positive maps on Hilbert spaces, to working with the Karoubi envelope of this. So in this category, objects are pairs of an object A from your original category and an idempotent E on that object. And then the morphisms of the Karoubi envelope are precisely those that are invariant under these idempotents. So we're able to describe situations where these idempotents are guaranteed to have occurred, guaranteed to have happened. But which idempotents are we particularly interested in? Well, the identity maps are quite interesting, and also, of course, the decoherence maps. So if one takes a full subcategory spanned by all the identity maps, then one can show this is equivalent to the original category, in our case CPM, and you get back all the quantum systems. And if one takes a full subcategory spanned by decoherence maps, one can show this is equivalent to R plus map, the real positive valued matrices, and thus we get back all the classical systems. Okay, so why was any of this important? Why was decoherence important? Well, it describes the transition from a quantum system to a classical system. Now, if we suppose that we had some post-quantum system, some hyperquantum theory, one that's in some way some extension of quantum theory, then we expect there to be some way of transitioning back down to quantum theory. And this is because quantum theory does seem to offer good predictions of the real world. It's right a lot of the time. If quantum theory is deemed to be just an effective theory of nature rather than a fundamental one, we need some mechanism that describes the transition between the two. And hyperdecoherence could be that this mechanism, and we call such a theory that has such a map a hyper quantum theory. Now, one might hope that we're able to impose many of the same constraints on this hyperdecoherence map as we did on a decoherence map. So, in particular, that it's causal and idempotent, these sorts of properties. But sadly, there is an existing a known no-go theorem which prevents this. And to be precise, if the hyperdecoherence map is causal and idempotent, if pure quantum systems are pure within your hyperquantum theory, if the maximally mixed quantum state is maximally mixed hyperquantumly, and if purifications exist in your theory, then it was proven that this map can't exist. It can't exist. But it seems that we might be a bit stuck here. And how we go about getting around this. And our aim essentially is just to try and drop at least one of these axioms, but being able to still give the map and the overall theory a sensible operational interpretation. So the theory in which we did this is based upon the CPM construction, but it's based upon iterating the CPM construction. So what is the CPM construction? I'll just give a very brief recap of this. Essentially, you start with the morphisms of your dagger compact closed category, which I'll draw here in grey wires, and then you fold these. And now, given these folded morphisms, one discards environment systems. So you discard E and E star using the cap. And then if, for instance, we started with the category F Hill with finite dimensional Hilbert spaces, then this resulting category is precisely that. The maps of this form are precisely that of the completely positive maps on Hilbert spaces. And this comes with its own set of string diagrams, which are the ones I've been drawing in white so far. So our aim is to, in some sense, do this again, to iterate this construction. So we looked at abstract, what we just did, and Stefano gave a nice way of looking at this in another work. And we can understand this folding step by essentially a group action by monoidal functors on your category. So one has a group homomorphism from Z2 into the automorphisms of C. So these are the endofunctors of C with two-sided inverse, and one sends 0 to the identity functor on C, 1 to the conjugation functor, and then given this group homomorphism, we're able to construct what we call the doubling functor, and this acts in precisely the way you expect. It sends A to A tensor A star, and similarly for morphisms. And now, given this sort of construction, we could generalize this and say, well, how about if we just took any abelian group G, any group homomorphism from that into the automorphism C? Well, then we could construct a more general folding functor. And we were particularly interested in a particular case of G, and that's when you take the group to be Z2 cross Z2. So this is simply iterating what we did before. So you sort of fold twice. Now that once one's done this, though, there's some amount of freedom in how do we join up, how do we discard these environment systems that we're left with. And there were sort of 3 choices that were of the many that you might choose that were particularly interesting to us. The first is to use caps, like in the first iteration of the CPM construction, and this returns the double dilated maps which have appeared before in the literature. Another choice is to take a spider, join up all your environment systems with the spider, and this returns the double mixed maps. And then there's another choice where you could use caps, but they're not the caps given sort of directly by duality of E and E star, but rather induced by having a special commutative dagger Frobenius algebra. And then you kind of join them up in this slightly crisscrossy fashion. Now, double dilation and double mixing have been considered before, and Zwart and Kircher have shown that, for instance, all the double mix maps of all the maps of the second form here can be written in the first form. So the theory of double mixing is a strict sub-theory of double dilation. And by a very minor alteration in what they did, you can show that the double mix maps can also be written as density hypercube maps. So it's a sub-theory of that as well. What's perhaps not quite so clear is whether double dilation and density hypercubes are the same. They both all just have caps going on. They look kind of a bit similar. Maybe they're the same. Turns out they're really not the same. They're really quite different theories. And I'll touch a bit more upon this towards the end of the talk. For now, we'll focus on density hypercubes. In the original work on density hypercubes, it was shown that they have hyper-decoherence maps, which I've put on the left here, and full decoherence maps on the right here. And since these maps are idempotent, we can do like we did before, work within the Karoubi envelope, splitting the idempotents. And then if one takes a full subcategory spanned by these hyper-decoherence maps, one can show there is an equivalence of categories to CPM, so you return all the quantum systems. Similarly, if you take a full subcategory spanned by decoherence maps, you get back R plus mat. And you can take, of course, the full subcategory spanned by the identity maps to get all your hyper quantum systems. But it was noted that there was a slight issue with the original work in that it was noted that the hyper-decoherence map is subnormalized. So this means it's not clear that they had a good operational interpretation. In principle, it was possible that they could occur as part of some larger map, but it wasn't really clear how this could be done within the theory. There was a few sort of questions here. So this is the first thing that we patch in this new work. We show that by adding an additional map to the hyper-decoherence map, we can complete it to a normalized one within the theory. So the important point here is that this second map that we've added is a map of density hypercubes, and since the theory is closed under sums in CPM, this new map is also one. I should note here that this completion is for the case where the dimension is only 2. The higher dimensions, it's in the paper for those who are interested. But why is this completion important? Well, it allows us to give the hyper-decoherence map a sensible operational interpretation, and that's as one outcome of this larger normalized map. So in fact, we have a notion of probabilistic hyper-decoherence within this theory. There's sort of a sector of theory which is accessed by hyper-decoherence, which gives a quantum theory back, and there's another sector which we refer to as the beyond. The other reason that this is important is because it allows us to complete quantum measurements to measurements on density hypercubes. So you can discard this above map, and you'll get some effects, and sort of the first two are the two effects that would be in this quantum sector, sort of the quantum ones, and then by adding this additional effect, which we call the unspeakable horror from beyond, we're able to complete measurements to proper measurement on density hypercubes. It's worth remarking upon where the quantum states live within this theory. Of course, that they are precisely the states which have been hyper-decohered, so they can take this general form. So one can show, for instance, that by doubling the quantum zero state, this is invariant under hyper-decoherence in this basis. And thus in some sense this really is quantum zero, and similarly for double one. So one might question, have we actually done anything here other than just double quantum theory? Are all the quantum states double of their version in normal quantum theory. And this is in fact false. So for instance, if you take the doubled plus state, this is not invariant under hyperdecoherence. So in fact, this is some hyperquantum state. And in fact, the quantum plus state is given by taking plus and injecting it into the larger theory. So now we have some understanding of how perhaps decoherence, hyperdecoherence could work within this theory. It's interesting to ask as well, what do we lose by decoherence? In particular, what invertible maps are quotiented away by decoherence, and this is known as the phase group. In quantum theory, these are precisely the phases that are sort of diagonal in the basis that you decohere in, and it gives you a group that's isomorphic to a torus, and these are often drawn as the spiders with the phases on. And we can ask a similar question for density hypercubes. What invertible maps are that are quotiented away by decoherence? And perhaps unsurprisingly, if you take the quantum phases and double these, one can show that these guys are indeed quotiented away by decoherence. But are there any more? Do we just have all these double quantum things? Is there anything else in this theory? And the answer is yes. So we can take these guys, and these are also quotiented away by decoherence. So we have some genuinely post-quantum phases within this theory. And one can look at what groups these form, and there's more details of this within the paper. And then one could ask the similar question, what invertible maps are quotiented away by hyperdecoherence? And one check that the first of these guys, the double sort of quantum phase spiders, are not quotiented away by hyperdecoherence alone. They're actually sent precisely to the quantum phases by it. But the second maps here are quotiented away, so we have something that really is sort of a post-quantum phase within this theory. And I will now finish up with a short digression into the theories of double mixing and double dilation. And it's interesting to ask how much of what I've spoken about here also carries across to these two theories. So for instance, can we find a hyperdecoherence map within double dilation? And one might think, well, can we just take the same map that we did for density hypercubes? In fact, you can't. It's not a map in these theories. So perhaps there's something similar that might work in a similar way, and there's maps that look kind of similar-ish. In fact, these just don't work, and we give an actual proof of why they don't work in the paper. But a simple reason, a simple non-rigorous way of seeing what goes wrong here is that the first map sends complex numbers and it squares them, so you get back something complex. So you have some hope of getting quantum theory, whereas the second thing sends complex numbers to real numbers, and there's no way you're going to get back quantum theory here. So while this doesn't, of course, prove that the double dilation does not have hyperdecoherence maps, it at least rules out many of the most obvious choices. But we can go a step further than this and ask, well, what invertible maps are available within double dilation? So when are these maps in double dilation invertible? Well, you can't have, since they're CP maps, one can convince themselves that you can't have these discarding maps, so they have to take the form on the right here. But then by unfolding this into F-Hilb, you see that really what we've got is a doubled CP map, and you can't have these discarding maps either. So the only invertible maps within this theory end up being precisely the doubled unitaries from quantum theory. So this means that even if this theory did have a hyperdecoherence map, there'd be no non-trivial phases for it to quotient. So in this sense, it would sort of be a trivial post-quantum theory. So I'll finish with a few remarks of where we hope to go next with this work. Firstly, a simulation of density hypercubes would be really quite interesting. So there's some evidence from the original work on them that they could exhibit higher order interference, and we'd quite like to see if we can verify this by simulating numerically the sort of interference patterns, the multi-slit interference patterns. Secondly, just simple studies of GPT-style properties. So do purifications exist within this theory? These sorts of fundamental questions. Three, this is particularly relevant if we're able to confirm higher order interference. We could then study the information theoretic capabilities within this theory. There's evidence to suggest that theories with higher order interference could exhibit beyond quantum information theoretic capabilities. So this is quite an interesting avenue. Fourthly, we're interested in variations on the current construction of hypercubes. For instance, one could try and describe the theory from the quantum perspective, from the perspective of a quantum observer within it, and this involves a slight variation on the discarding map taken for the theory. These sorts of things would be quite interesting to see. Can a quantum observer see post-quantum effects within the theory, or do you have to be someone who is as part of the hyperquantum theory? It'd be interesting to see. And finally, sort of theoretical investigations of probabilistic hyperdecoherence. So can we study this in a theory-independent way? Can we refine the no-go theorem from that I mentioned before? So I will end there and see if there's any questions.
All right, thank you so much for the talk. I see a few questions in Slack, so maybe I should start from the first one. So,
Right.
or maybe did someone answer that already? I'm not sure. Okay, let's just ask it anyways. It's from Eddie Cavalcanti. And actually, there's like two questions there. The kind of simple one is whether post-quantum and hyperquantum are synonyms or if they are some kind of different.
So I've been using them interchangeably here, yeah.
Right. So his question is it necessary that if nature is described by some post-quantum theory, quantum theory emerges through a hyper-decoherent process? Couldn't it be due to some limitation on operations available to us for other reasons, say because some dimensions are compactified or something?
Yeah, so there are several possibilities. One of which could be a hyper-decoherence map. There are of course other ways that this could occur. I mean, I will point out that actually there is another way of interpreting. If I go back to, there are a few ways of sort of looking at what we've done here. I mean, one is that you could interpret this as a probabilistic thing in the way that I described. The other way is to say, well, actually, we could be confined to the quantum sector of this theory. And in this way, this is not that dissimilar to these ideas of compactifications and dimensions that aren't accessible to us. We could be confined to the quantum bit of this rather than the beyond bit. Can we see the post-quantum effects from this theory? So there are notions of that in this work as well, I would argue.
All right. So next question is by John Selby. So it says that the only other hyperquantum theory that I know of is Valentini's out of equilibrium Bohmian mechanics. Do you have any idea if this can be understood categorically and whether the equilibration process can be understood as a hyperdecoherence mechanism?
The answer is I don't know, I'm afraid. We should chat about that. It sounds interesting, but I don't know, I'm afraid.
All right. Then Cole is asking whether you completely characterized the phase group.
No. So we think we know. We think we know it. We know it for the smallest dimension, and we can convince ourselves why it is what we claim it is in the paper. For the larger dimensions, we show that there exists post-quantum phases, and we find quite a few that are not part of normal quantum theory. But I don't believe at the moment that we've actually found them all, and we don't prove that. I think that there could exist more within this theory, and it'd be quite interesting to see what these could be.
All right. So the next question, and I think it's the last question that there is in Slack, is by John Selby. He asks whether you have looked at what the other branches, i.e. the beyond, of your hyper-decoherent mechanism looks like, and i.e. are they just another copy of quantum theory, or are they some other GPT?
Great question. We're not entirely sure, and I think it will depend upon the dimension of your system at the beginning. I mean, in the smallest case, when the dimension of H is only 2, the beyond seems to really just have one, if I remember correctly, one part to it, and in this way, it might be kind of quite a trivial extra part to the theory. As the dimension increases, it does seem that there could be many pure states that exist within the beyond, and it could be some non-trivial sector of the theory, perhaps equivalent to quantum theory. Again, we're not entirely sure at the moment. As I say, it does seem to depend upon the dimension you start with, things like this, depending on the Hilbert space.
Okay, so I think you've answered all of the questions that you've got so far. So maybe we can stop here and we can thank you and all of the speakers of the session again. And clap. And yeah, you can continue discussing things with people on Slack. So I think
that sounds great. Thank you very much.
Be there like for the whole week. So all right. See you when the conference resumes after the lunch break.
Great. Thank you very much.